2, 1, and we are live. Hello world, it's Siraj, and welcome to this live game show. In this episode, we are going to build a quantum classifier together, and that's what you're seeing right here next to me. This is a simple quantum classifier that I built using the PennyLane library. This is a quantum neural network free library that anybody can use. It's available on the internet, and I'm going to show you exactly how to use that to build your own custom quantum neural network. Now, I know that this might seem a little daunting, but it's not. Trust me, it's actually pretty easy. We just have to go through a few concepts before that. And guess what? Someone's going to win $500 in the next hour if they can answer all 3 of my questions. But in order to answer my questions, they have to pay attention to this. All right. So we're going to go through a lot of concepts in a short amount of time. And guys, my internet is kind of spotty today. So if anything goes wrong, trust me, I will create another version of this video. This information is far too valuable, fully edited, and without any hiccups, all right? So if something goes wrong during this live stream, don't worry, I've got you, all right? We're gonna create the world's most valuable esport over the next 5 to 10 years, slowly by creating these winners, people who win my games, one by one, for cash prizes, where I'm really focused on the cash prizes for you guys. I wanna reward you guys for having subscribed to this YouTube channel, all right? So where do we begin with quantum classifiers? I mean, there's so much theory behind quantum computing. There's so much theory behind machine learning. And how are we expected to combine these two ideas together? Well, I want to start with a very application-focused problem for you. Okay, we're just going to focus on one thing. I'm not going to go into what's a qubit. A qubit is a 1 and a 0 at the same time, what everybody does. I'm not going to do that. We're not going to rehash quantum mechanics and stuff. We're going to focus on a simple problem that you and I can sit here and solve together. And that problem is we want to break Bitcoin. Mic drop. We want to take all of the Bitcoin from Satoshi Nakamoto, the creator of Bitcoin, from his account. That's our job today in this live stream. And we're going to use quantum machine learning to break the entire Bitcoin network. Let's see if we can do that together. All right. So how are we going to break Bitcoin? That's our task for the next hour. We're going to try to break Bitcoin. And Bitcoin is one of the most powerful networks in existence. Now, I literally wrote a book on this, right? So I'm not going to sit here and talk about all the details of Bitcoin, but I will talk about one part of Bitcoin that is relevant to us. And that part of Bitcoin is the public-private key pair generation. So anytime that you create a Bitcoin wallet, your own bank account right on your phone or laptop, you get 2 sets of numbers and letters. Those are called your public and your private key pair. Now, with your public key pair, anybody can send you money. So if I want to give you my public key pair, those 25 characters down here, then you can just send me as many Bitcoin as you want. But if I give you my private key pair, then you can steal my Bitcoin. So I don't want to give you my private key pair. Now, that's the basic idea behind Bitcoin security. Your public key pair, people can send you funds. Your private key pair, you never want to give that out. And those 2 key pairs are generated using an algorithm. Now, what algorithm is Bitcoin using to generate the public and the private key pair? Well, it's called the RSA algorithm. Now, I know that there's a lot of text right next to me, and guess what? I don't want you to care about any of that. Don't look at any of that. All I want you to look at is the first line. That's all we care about. So RSA is the algorithm that Bitcoin uses to generate a public and a private key pair. And RSA stands for the initials of the inventors of the algorithm. I think it's like Ramir, Shamir, something like that. It doesn't matter. But the first part of the RSA algorithm is to start with 2 large prime numbers. Now, recall, prime numbers are numbers that don't have any factors. The only factors it has are 1 and itself. Nothing else. It has no multiples. 2 doesn't divide into it. 3 doesn't divide into it. Nothing divides into it. So what's a prime number? 7 is a prime number because what divides into 7? 1 and 7. What's not a prime number? 8, because what divides into 8? 2, 4, and 8. You see what I'm saying? That's what a prime number is. So the RSA algorithm generates a public and a private key pair starting with 2 large prime numbers. So we don't know what those prime numbers are. We just know what Satoshi's private key is. But assume we did know. Assume we knew what those 2 initial prime numbers were. Then we could reverse engineer the RSA algorithm to find out what the private key pair is. That's the idea. If we can find what those two prime numbers are, then we could reverse engineer and find that private key from Satoshi. Now, that is a really exciting idea. The idea of being able to find out what the private key is for such a valuable Bitcoin address. Now, if we figure out how to do this, we're going to immediately give this solution to the Bitcoin Core developers so they can patch it, because we want a quantum resistant Bitcoin blockchain, because we love Bitcoin. We don't want to destroy Bitcoin. Actually, we want to security test it. So we need to find out what those prime numbers are given a private key. How do we do that? Well, this is, a big part of this problem of finding out what those two initial prime numbers are is the prime factorization problem. That's a huge part of that problem. So we're going to focus on that part of the problem. So prime factorization means, can we find all the prime numbers in a given sequence of numbers? So let's say, give me all the prime numbers up to 10. Let's see, 1, 2, 3, 5, 7. That's it, right? Those are the only numbers without multiples. Now, give me all the prime numbers up to 1 million. You can't do that using mental math, right? So we need an algorithm to do that. So let's look up an algorithm that's going to help us find all the prime numbers, all the prime factors of a given number. Let's go look this up. So the first thing we want to do is we want to go and find an algorithm that does this. I mean, there's so many potential algorithms that could help with this, but there's one in particular that I really like, and you may or may not have heard of it. It's called the sieve of Eratosthenes. So I'm going to say that again, sieve of Eratosthenes, ancient Greek, beautiful language. In fact, it's an ancient algorithm. Algorithms can be ancient too. Algorithms are all around us. Just computing is one way of making them repeatable and letting us engineer them, but we are not in control of all algorithms. Some algorithms are outside of our control. Back to this. So the sieve of Eratosthenes consists of 5 steps, and we're going to write out the code for this in Python together. We're going to write out simple sieve of Eratosthenes code for prime factorization, because we want to break Bitcoin, because we love Bitcoin. The first step is to create a list of consecutive integers 2 through n. So let's say n is 10. So 2, 3, 4, 5, 6, 7, 8, 9, 10. The second step is to initially let p equal 2, the smallest prime number. So okay, p equals 2. That's it. The third step is enumerate the multiples of p by counting in increments of p from 2p to n. So that goes 2p, 3p, 4p, 5p, 6p, 7p. So if p is 2, what are those numbers? 2, 4, 6, 8, 10, 12, all the way up to all the multiples of 2 up to n. Number 4 is to find the smallest number in the list greater than p that is not marked. If there was no such number, stop. Otherwise, let p now equal this new number, which is the next prime, and repeat from step 3. When the algorithm terminates, the numbers remaining not marked in the list are all the primes below n. So that might seem kind of confusing to you, but luckily for us, Wikipedia has this other way of explaining the sieve of Eratosthenes, and it's right above me. I want you to read this together. It's a little poem. It says, sift the 2s and sift the 3s, the sieve of Eratosthenes. When the multiples sublime, the numbers that remain are prime. Now, that is a beautiful poem. I love that poem, and I see some smoke coming in my backyard. Hopefully nothing's on fire. Okay, we're fine. If anything's on fire, it doesn't matter. We have a live stream. Priorities, people. So that's the sieve of Eratosthenes. But basically, we're looking for all the multiples of 2 and 3 up till n, and then we want to slowly increment and find all of those prime numbers up till n using 2 and 3. And if we can do that, then we will find all the primes up to n. So that's the idea. So let's code this out using a Google Colaboratory, which is essentially a Python notebook, a Jupyter notebook in the browser, which is very, very simple and easy for us to use. So our first attempt here is going to be to program the sieve of Eratosthenes. So let's just program the sieve of Eratosthenes together, and we'll see if it works out. So the first thing we're going to do is we're going to import sys, simple library, and we're going to define all of our, let me make this bigger. We're going to define all of, okay. We're going to define all of our code here. So this is a factorizer. Remember, this is a part of the big problem of breaking Bitcoin. So everything's going to go in this factorizer function. So the first thing we're going to do in the factorizer function is we're going to say, given n is our number that we want to find all the prime factors of, we're going to start with an empty list. So this empty list, we're going to start off with the number n. We're going to typecast it using int. And then we're going to create an empty char array, which we're going to fill with all the prime factors in a second. So let's do our first for loop. So in our first for loop, we're going to go through 1,000 numbers. Let's just say arbitrarily 1,000 numbers. We can increase this in a second, but we're going to go through 1,000 numbers and we're going to initialize those as empty numbers. That's our first step. Our next step is to create a list of all the multiples of 2. So remember, in that sieve of Eratosthenes pseudocode that we just read, we want to find P, we want to define P. P is going to be 2. And then we want to find all the multiples of 2. So 1 by 1 by 1 by 1 by 1. We will define all the multiples of 2, and then we're going to divide all the multiples of 2 1 by 1. So while k times j is less than or equal to n, and we're going to continually multiply k by j, where j is going to increment in factors of 2. K plus equals 1, right? Because we're going to increment slowly. And there's one more loop we have to do, and then we're done with the sieve of Eratosthenes. And that is, now that we have all of those multiples of 2, let's print out all the prime numbers that were not multiples of 2 or 3. And the reason is because prime numbers are unique in that they are not multiples of 2 or 3. Every other number is a multiple of 2 or 3 except for prime numbers. And so we have now printed all that out, and we can return the total. Of course, there's going to be an error here. Make sure that that's all visible. Of course, there's going to be an error here. There's no error, so that's great. So let's try out our algorithm. What do you say? Do you think this is going to work? Let's see if this works. So if n equals 9, what are all the prime factors? Say them while I print this out. Hopefully this works. Hopefully the sieve works. Factorizer n. Here we go. Here's our algorithm. What? L is not defined. Factorizer n. Line 20. That's I, not L. That's what that is. That's what that is. Okay. Now what's the problem? L is not defined. Okay, I see it. L again. I don't know why I put L. I should put I. Alright. Now let's try it. 2, 3, 5, 7. There you go. I mean, I should have put spaces between each of those chars, but those are the prime numbers up till 9. Now, let's switch this up. Let's say that instead of, remember, in RSA is not using the number 9. RSA is using 2 very large prime numbers, like giant prime numbers. So if we want to find the prime factors of giant prime numbers, let's put in 9 million, 9 trillion, whatever, 9. What's going to happen is we're going to have a Stack Overflow, list assignment index out of range, which means that we have to increase this 1,000 up to a really big amount. And even then, it's going to take a long, extremely long time. That's going to take longer than the age of the universe, if it's a big enough number, like a really big number. So we have a problem here. Like the sieve of Eratosthenes is not going to work for us. We are screwed in terms of the sieve of Eratosthenes. So we need to figure out what to do instead. And so I have a better solution than the sieve of Eratosthenes. Now, I'm going to need your help for this better solution. So in order to find the better solution, I'm going to ask you a question. And the question is, where's my thing? What is one way we could possibly improve the time complexity of our prime factorization algorithm? I'm not sure why I'm not seeing this overlay like it always should. If that's the case, that's fine. I'll just figure out hacky solution here. Give me 1 second, guys. We're going to get these questions up for you. I want you guys to see people putting the answers in. Okay. Here you go. So the question is, what is one way we could possibly improve the time complexity of our prime factorization algorithm? Should we use linear regression? Should we use quantum? Should we use blockchain? Or should we use k-means clustering? How should we improve the sieve of Eratosthenes? Like, we want to break Bitcoin. How are we going to do that? I see that most people are answering one question here. Most people are answering a single question, a single answer. So, but one person's answered something else. So I think most people have the right answer here, which is good. And meanwhile, while you guys answer these questions, let me answer any questions if you guys have any. I'm not seeing any super relevant questions right now. But meanwhile, can't believe this overlay didn't work this time. That's sad. You know, live streams, not everything always works perfectly. But that's okay. We could still see this. So let's see the answer now, guys. I'll give you guys 30 more seconds while I talk a little bit more about what we're going to do now. So we tried out the sieve of Eratosthenes. That wasn't good enough. And so we want to improve it. Now we're going to use one specific technology to improve our prime factorization problem because we care about real world applications. There's one question that I am seeing right now that seems relevant too. I'm going to answer those and then we're going to move on. Is this the algorithm you wrote the paper for? No, it's not. This is not the algorithm I wrote the paper for. That was a bunch of Google Translate, and it's been a year since then, and autocorrect, and like complicated Hilbert space. Complicated is not a word. It's complex Hilbert space. We actually will be talking about that in this live stream. What else did I get wrong in that paper that became a meme? There was like complicated Hilbert space. It should be complex Hilbert space. Oh, logic doors. It should not be logic doors. They're logic gates. And that's actually what the song at the end is going to be about when I freestyle for the winner in tribute. The mind is a muscle, and so you break logic doors. That's the line. So Harshit, related title said Python syntax. Good to see you again, related title. He said Python syntax always confuses me. Look, really, because I think of it as more readable, but I will keep that in mind. If I see enough people complaining about Python, we'll just switch over to C. I am language agnostic, guys. We care about algorithms. We are not some kind of tribe for a language or anything. We care about algorithms and the most efficient way to write them. Okay, so let's see what the answer was. Now that we have like 35 people who have answered this. The answer was B, quantum. That's what we're going to use to solve this. Okay? Quantum is the answer. Always. Always. So if you got that right, good job. Hopefully that wasn't too loud. Let me lower that volume. Sorry, guys, if that was too loud. Okay. So we're going to have to use quantum to solve this. So let's use quantum to solve this together. All right. So, oh my God, there's so much I need to tell you now about quantum. Okay, how are we going to solve this? Well. I have some math for you people. I hope you're ready for some math. But before we get to the math, I just want to very briefly show you Shor's algorithm. This guy Shor, what a G. In 1994, Shor was trying to solve this problem as well. He was trying to solve the problem of prime factorization. How do we efficiently calculate all the prime numbers up to a given number? And he made this wonderful algorithm in 7 steps called Shor's algorithm. And He called it Shor's algorithm. We're going to talk about Shor's algorithm in detail, especially the quantum aspects of it and why quantum computing is necessary for Shor's algorithm to work properly. And I know this might seem a little mystical, so we're going to go through this kind of slowly. But before we get into the math, I just want to read out the 7 steps of Shor's algorithm with you here together. And I'm going to make them a little bigger because I really want you to get this part. So Shor's algorithm has 7 parts. The first part is to pick a random number. We can do that, right? Let's say we want to factor all the prime numbers up till n. So up till n, and n is 10. So the first step is to pick a random number. Let's say, I don't know, 6. Then the next step is to compute the greatest common denominator of that number and n. So 6 and 10. Now, there's a lot of ways to do this, but the one way to do this that Shor uses is the Euclidean algorithm, and we can just treat that as a black box, but assume that we found the greatest common denominator of both of those numbers. That is the biggest number that divides into both that random number and our number in question, n. The third step is to say, well, if the greatest common denominator is not equal to 1, we're done. We found all the prime factors. Otherwise, we're going to use this function, this magical period finding function, to find all the prime factors. And we're just going to call it this magical function. It's a black box. We don't care about it. It's step 4. We're going to go right to step 5, 6, and 7, and then we're done. Step 5 is to check the outputs of that period, that wave, that sinusoidal function, that Fourier-like function. Number 5 is if R is odd, if one of the outputs is odd, return back to step 1. Step 6, if AR divided by 2 equals -1 mod n, go back to step 1. Again, just a random series of operations. Number 7, the last step, if the factors of n are the greatest common denominator of these 2 values, we are done. So essentially, it's a bunch of operations that are being applied to our number n and a random number that we generate. The greatest common denominator function is just embedded inside of this algorithm as a Euclidean algorithm. But the real key of Shor's algorithm, the real mystery, the black box of Shor's algorithm, is this period finding routine right here, a to the x mod n. Okay, now that seems very, very, very confusing, because what does a period have to do? And I'm so excited to explain this part to you because I understand this. And that's only because I think the only reason that I fully understand this is because I've been looking at machine learning for so long and quantum computing and all this stuff. And so I'm going to explain exactly what this period finding algorithm does as best as I can. This is going to be quite a challenge, but I am ready. This is the kind of challenge that I love. So let's get our markers ready and let's bring up the math cam. Let's bring up the math cam. Okay. All right. So. What do I want to show you here? Well, where do we even start? The place I want to start is with probability theory, because we love probability in machine learning, right? So assume that we want to find the probability of a coin flip. Let's start with a coin flip. The probability of a coin flip is going to be equal to probability of heads plus probability of tails. So that's like a really simple way of measuring probability, right? We're just writing out probability in that way, which is pretty simple. But there's other ways of writing out probability. Like we don't have to write out probability in that way. We can write out probability as a series of states. So we can say that we want to find the probability of, I might be getting some questions here in a second. We can write probability. What else can we write? We can write out. So first of all, let me talk about the math that we're about to use. We're going to use linear algebra. We're going to use probability. and we're going to use eventually calculus, but that's for the gradient-based optimization part at the very end. Right now, we're just focused on probability, right? I just showed you a little bit of probability. Now I want to show you some linear algebra. So if we have some scalar number m, okay, we have a scalar number m, we might want to multiply m by a vector. And this vector is going to contain a bunch of numbers, 1, 2, and 3. Okay, so that's m times 1, 2, and 3 is going to be equal to another vector. And we're going to call the outputs of this vector a, b, and c. And so we have m times 1, 2, 3 equals abc. This is a matrix operation. We're performing a multiplication operation between two vectors. These are groups of numbers together. And the great thing about linear algebra, one of the great things about linear algebra, is that it provides us with this set of operations that we can use. Hold on, it's going to be black for a second. It provides us with a set of operations we can use to multiply groups of numbers together, not just single numbers, but groups of numbers together. And that's really powerful because we can say things like 1, 0, 1, 0, times, I'm going to make this really straight, times 0, 1, 1, 0. We can actually do that with linear algebra, right? So it's like this part times this part, and then it's like this part times this part, and then this part times this part, and then this part times this part, and the result is going to be a 2x2 matrix. That's linear algebra. So I just wanted to really briefly show you, define linear algebra and probability theory for you for the next part of this, because we're going to use linear algebra and probability theory for this part, which is what I'm going to show you right now. Okay, so that's linear algebra and probability theory. Now, why does that matter to us? Well, there is this idea called the Fourier transform. And if you don't know what the Fourier transform is, it looks like a sinusoidal wave. It's like a wave like this. And it's going to be a function, a sinusoidal function, like cosine of x or sine of x. It could be anything like that. So let's just say that this one is called sine of x. What the Fourier transform does is it helps us define the parameters that we're going to need for Shor's algorithm. It's essentially a linear transformation on this function. All of deep learning is essentially a bunch of linear algebraic operations. And that idea of linear algebraic multiplication, addition, we're going to apply to quantum computing. So now that I've talked about probability, I talked about what linear algebra is, I defined what a sinusoidal function looks like. Now we can finally talk about all of that in the context of Shor's algorithm. So in the context of random drawing, in the context of Shor's algorithm, here's what that means. Steps 1, 2, and 3 were just normal, find the greatest common denominator. Remember, step 4 was that weird part. We wanted to define this transformation function. Now, what we can do is we can define this transformation function as what's called a quantum gate. And a quantum gate is essentially, think of a logic gate, a normal Boolean logic gate. It's got a true or false statement. A quantum gate isn't just true or false. So a normal logic gate is going to be, you have some data and it's flowing through this graph, and then you hit this Boolean logic gate. And it's going to say true. Let's just say, in this case, it's going to say true. And then it's going to hit true, and then it's going to output something. It's going to be true. That's normal Boolean logic, right? But in quantum computing, a quantum gate isn't just true or false. It's going to be something else. It's going to be a black box that's going to have a set of values. That's essentially all it is. It's just numbers. Numbers are in here. Numbers 1, 0, 0, whatever these numbers are. But we call these numbers one of two things. They're either in a superimposed state, so superposition, or entangled. Those are the two primary, those are the two primitives, superposition and entanglement, that we are adding to our programming vocabulary for Shor's algorithm. Now, which of those two applies to Shor's algorithm? We're not even going to worry about entanglement. That's not even in this video. All we care about is superposition. The idea is that if we take whatever some input is and we perform a certain linear algebraic operation on it, then the result will be a superposition of possibilities. Now, that's what I want to talk about right now. That's the weird part. That's the almost unbelievable part. Like, what? What? Here's the idea. We have some possibility space of answers for what the prime factors could be. Okay? They exist, right? All numbers exist somewhere in the universe. And so we have this possibility space of numbers 1, 500, 5, 5, 5, 5, 6, 7, 8, 9. All these numbers exist. 32. And we have to predict what the prime factors are going to be, right? Because we live in a deterministic world and we think in terms of quantum mechanics, like force equals ma, right? Newton's laws. But at the smallest scales of reality, this idea of superposition applies. And the word simultaneously is thrown around by every pop sci YouTube video or every pop sci article, but it's more than just simultaneously. It's not just 1 and 0 simultaneously. It's accessing parallelized timelines across different spaces to compute what the prediction should be. Essentially, what a superposition does is it's like a web of possibilities that we can pre-compute before we even find the answer fully. But these are all like waves. Like there's a 30% chance the answer is going to be 1. There's a 20% chance the answer is going to be 5, 5, 5. There's a 32% chance the answer is going to be 6, 7, 8. That's what quantum computing is going to spit out for us. And then we have to pick the highest probability one. So you might be thinking, how the fuck is it able to predict what the answer could be, all the possibilities? Is this some kind of time-traveling machine? No, it is not a time-traveling machine. It's accessing parallelized timelines to compute this. Now, on a simulator, it's not actually doing this because you need what are called qubits that are using superposition in hardware to compute this. But we can simulate the idea of superposition using classical mechanics, transistor-based classical computing, the same way, in that the result isn't going to be the true amplitudes. The words are amplitudes. I'm just going to keep talking. You're going to get this stuff eventually. It's not going to output the true amplitudes because there's no way to predict that without true hardware superposition. It's going to predict what the amplitudes could be, so they're just random number generators. So quantum simulators are fun for research, but if you actually have access to quantum hardware with enough stable qubits, and I say stable because that's where the idea of entanglement comes in. We want to minimize decoherence, and that's really hard. That involves quantum error correction. We want to keep a quantum computing system stable. Supercooling has to be there. There's a lot of techniques to make sure that quantum computing is stable, and that's an area for the future. Does quantum computing work right now? No, it does not. But could it work for the future to make machine learning algorithms more data efficient, require less energy, require less power, become more accurate, become more robust to perturbations? Yes, absolutely, I believe that. And lots of money is being thrown in that direction. So back to this. There's actually a possibility space of answers that Shor's algorithm can look at for all the possible prime factors. And what the quantum Fourier transform, that's one of the functions, that's the key part of Shor's algorithm, the quantum Fourier transform. What it does is it finds R, it estimates R, and R is the period. It's kind of like a clock. It's looking at along this period that essentially the best way I like to think about it is that it's accessing parallelized timelines across different spaces. So I guess I have the many worlds interpretation of quantum mechanics as I'm using the PennyLane quantum computing library, because that's what makes the most sense for me, because I don't think this is doing time travel. I think that there are multiple spaces across reality, and through superposition, we can actually retrieve scalar values, as crazy as that sounds, from these parallel timelines, and then use those scalar values instantly to improve the predictions of our models. And so the quantum Fourier transform is spitting us back all of those R's, those R values, the possible prime factors of our number n, and then we have to decide smartly using our algorithm which is the most likely. Now, that's the idea. So Shor, let me go back to me now, because I have a lot more to talk about. So Shor actually proved in 1994 this idea of a quantum algorithm, that we could code this out on a classical computer. We could do that, you and I. But and it would work, and it would compute properly. But if we want to simulate, if we want to use the magic of superposition, and we want to actually find the answer in not n cubed time, not in n squared time, but in something really fast, in say log n time, then I think Shor's algorithm is log n. Correct me if I'm wrong. It's definitely faster than the sieve of Eratosthenes. And, there could be an algorithm that's faster than Shor's. But the point is that we're going to talk for 5 more minutes, and then we're going to code out this algorithm, Shor's algorithm. So the point is that Shor's algorithm, it uses this idea of a quantum gate, which is essentially a software construct. A quantum gate is something we build with software, and it has nothing to do with hardware. There's nothing mystical about it. It's essentially just a set of math operations. And normally with linear algebra, we just multiply matrices and neural networks. But when we apply linear algebra to quantum data, that means data that's in a superposition, data that has imaginary numbers in it, then we call that a complex Hilbert space. It's a complex Hilbert space. So that's a specific type of linear algebra that we're using to repeatedly apply a chain of operations across quantum gates. And so quantum gates use a specific type of linear algebra, like involving Hilbert algebra, it's what it's called, to make computations. We can run those computations on classical machines, which we're about to, and they can work. But if we really want the best results, we need to run some quantum hardware. So all that is to say that we now need to code this. I know what you guys like to see. We got to code this, guys. So let's get back to the code. We are now going to code out Shor's algorithm together. And we're going to code out Shor's algorithm using no quantum computing because, again, I just want to show you that we don't need a quantum computer to do quantum computing. Quantum computing is orthogonal. It is unrelated to quantum hardware. That just helps us get the speed up we need. But quantum computing is essentially a theoretical branch of computer science that involves using linear algebra in complex spaces involving imaginary numbers. That's really the key bit. Imaginary numbers are what we're adding to our jumble of linear algebra when we are doing deep learning. That's at the very end. We're going to combine quantum computing and neural networks together. But let's now code out this algorithm, and then I'm going to ask you some questions about what the next step is for us. I'm going to ask you about imaginary numbers. So I hope you're ready for that part. All right. So the next step is for us to write out some code here. So let's write out some code for Shor's algorithm in NumPy. Make sure this is big enough for us because we are trying to break Bitcoin, guys. We love Bitcoin. We want to break Bitcoin because we love it. Security testing. So the first thing we're going to do is we're going to import NumPy. Of course, that's it. And now that we have NumPy, we are going to we're going to think about what the answer is for this one. Hold on. There's some really great questions here. So I'm just going to actually show you my code rather than typing it out. Quantum Fourier transform, I want to answer some questions. I want to make sure we have enough time. So here's the code for here's the code for Shor's algorithm. Hold on. Make sure this is all in line. I want to read out this code to you. It's only 50 lines of code, which is totally doable. You ready to read this together, guys? So in the first step, in the first part of this code, there's a lot of things we might want to do. Wow, this kind of like froze. Hold on. Why did this freeze? Hold on. Okay, there we go. In the first part of this code, feel like this is like broken or something. Hold on. Why is this not working? Hold on. Guys, we might have an issue. I think we're fine. We're fine. Here we go. If you look at my gists on GitHub, they're private right now. I'm going to make them public. Don't worry. I'm going to make them public. So we start off with this Hadamard gate. I know that seems like a complicated word. Don't worry about it. Again, it's a quantum gate. Remember, all we care about is that a quantum gate is a logic gate. We know what Boolean logic gates are, true or false. They've got some set of math operations. A quantum gate uses quantum mechanics. And specifically, it's going to use a specific type of linear algebra, Hilbert algebra. And what a Hadamard gate is essentially just a matrix of values that when applied, so that when I say applied, I'm talking about matrix multiplication. When applied to some vector, it's going to turn it into a superimposed state. So a superimposed state of numbers. So it's essentially just a matrix times matrix. It's just matrix multiplication like we're used to with deep learning, except the terminology is different and the type of multiplication is different because the type of vectors are different because they're quantum state vectors which contain data which represents superposition, which is a possibility space. Superposition is a possibility space of different values across timelines. I really hate to even say that, across timelines. It sounds so sci-fi. I really can't think of a better way of saying it, though. I mean, I've been reading Scott Aronson's blog post, wonderful blog posts on quantum computing for the past few days. Professor of quantum computing at University of Texas, probably the biggest thought leader in this space. And so essentially, we take our input data, right? That's the number n. We apply a Hadamard gate to it. So then that's going to give us a possibility space of the period for that quantum Fourier transform of what all of those possible values are. And then using those, we can find all the prime factors. And so that's essentially what it is it's the quantum Fourier transform applied to some quantum input vector using NumPy, defined with NumPy. The quantum Fourier transform is what uses the Hadamard gate to compute the superposition. And that is the basic idea behind Shor's algorithm. Now, Hadamard is one word you're going to keep saying over and over again because basically any number, any vector, if you multiply it by the Hadamard gate, it's going to go into superposition. And we often need superposition to find out what multiple predictions could be. So now that we did that, I want to get to this question 2 now, before we get to the last part, which is quantum neural networks. I know what you guys want to see. So on to the next question. I'm going to begin accepting answers for the next question right now. And the next question you can see right here. It's a math input question. What is the square root of -9? This might seem totally random for you, but it's not. It's going to be related to what we're just about to talk about. What is the square root of 9? Seems like a simple question, right? It's totally related to what we're going to talk about. So the square root of -9. Let's see what people are going to say for all this. Most people have an idea of what the answer could be. So let me start answering some amazing questions. Some amazing questions are coming in right now. Someone's going to win $500 by the end of this, by the way. Harshit, quantum entanglement to reduce state space. Quantum entanglement doesn't reduce state space. It can actually increase state space as well. Is entanglement a form of dimensionality reduction? You know, I don't know the answer to that question, but I think that's such an interesting area of research. Guys, if I was going to do like a PhD in machine learning, I promise you it would be in quantum machine learning. And it would be with like generative adversarial networks using superposition to, here's going to be the crazy part, predict what, quantum language models. That's what I would build. You guys know what I would build, a quantum language model. What if we could use superposition to predict what someone's going to say? A word prediction engine that's not just predicting next words based on the previous words. It's predicting the next words based on the quantum state vector of what's learned throughout time. So it's looking through timelines to predict what the next best word could be. Is that even possible? Great idea. Switch to Rust. Yves, you know, just because you've been here and you're a regular, I might just switch to Rust. I will really consider that. Just program. Python is amazing, except how slow it is. True that. I agree with you. Neil Patel, that sounds from Fortnite Victory Royale. That's correct. I love Fortnite. Fortnite is a phenomenon, and it's a modern phenomenon of attention and engagement and glory and fun. And I want to use the concepts of Fortnite to evolve computer science education. Guys, we are going to create the most valuable esport on the planet. It's a 10-year plan that I have, and I'm really just getting you ready for this most valuable esport called Code Royale by giving you guys cash prizes and just showing you how the hardest problems in computer science can be gamified, and that you should study them and just stay on the path. No matter what happens, stay on the path. 2 more questions, and then we're going to answer this question, move on to quantum neural networks. Boise Data Science Meetup, shout out to Boise, says, I want to see a quantum comic by Siraj now. That might happen in the future when I have more... I'll make a video comic. Period is a distance from crest to crest or from tro to tro. It is, oh my God, I forgot. Isn't it both? Isn't it a generalized variable? Related title, can you share the Jupyter Notebook? Yeah, I'm going to add it to the video description right after this. Sudanva, can you apply quantum ML to reinforcement learning? Yes, of course, Sudanva. I think that would be really fun for Unity machine learning, integrating that with the PennyLane library, which is the one that we're going to integrate right now. Let's now see the answer. 24 people picked one answer for the square root of -9. Seems pretty easy, right? Square root of -9. Type it into your calculator. You'll probably get the wrong answer. So let's now see what the answer is for the square root of -9. Finish and reveal. The answer was 3i. I don't know who put -9 to the 1/2, but the answer was 3i. Most people got that. That's what I like to see. Most people got that. So that's good. And so now we have one more question that we're going to move on to. I don't want to spoil it, so let's get back to this. What's next, guys? The next and last part are quantum neural networks. I have been waiting to talk to you about quantum neural networks. Let me tell you, quantum neural networks. We just saw Shor's algorithm. We saw how Shor's algorithm used the period finding algorithm, the quantum Fourier transform, to predict a possibility space for what the prime factors could be using the superposition the linear algebraic idea of superposition encoded in a state vector. Again, vector multiplication. That's it. We're using different terms here. Quantum, superposition, Hilbert, complex, but still just matrix multiplication applied to probabilities. Now, what does this look like in the context of neural networks? My favorite topic. And let me also run the Victory Royale sound effect for those who got the answer to that correctly. Good job. What does it look like in the context of quantum neural networks? And that is what we're going to answer with a little bit of math and just a little bit of math. So let's put a little bit of math up there. A little bit of this, a little bit of that. Bada bing, bada boom. We got some, some quantum. Bada bing, bada boom. Hey. Okay, so quantum math, quantum neural networks. Okay, so quantum neural networks. So remember how I said how we have to use this specific type of linear algebra for this quantum state vectors that encode superpositions? Well, there's actually a way to think about that is really useful. And the way to think about that is that we have some input vector. So we've input vector F. We have a quantum circuit, QC, and then we have an output, FG. Now, you're going to see these like curly bracket notation. It's called ket notation. It's used a lot in quantum computing. But essentially, what we want to do is we want to create a quantum state vector. We want to create a quantum circuit. a quantum circuit is something we could do. We actually just did that for the for Shor's algorithm. The quantum circuit was the quantum Fourier transform. This quantum circuit could be anything, this box. It could be superposition, it could be entanglement, anything that uses math from quantum mechanics, essentially imaginary numbers. Now, one of the simplest types of quantum systems is the qubit. Now, again, everybody and their mother has talked about what qubits are. It's 1 and 0 at the same time. Blah, blah, blah. But essentially, one way to think about the qubit is that it's operating in this three-dimensional space of imaginary numbers. So one dimension are imaginary numbers, and the other dimension are real numbers. And so it's like this 3D space, and we can call it a block sphere. And so we're trying to find the values in that possibility space of the qubit using superposition inside of this quantum circuit. Now, what else looks like a quantum circuit? You might recall that there's this funny little idea that called deep learning, where you have some input vector f, so I, or we'll call it I, and you feed it to this neural network. And what this neural network is going to do is this neural network is going to spit out an output. Now, what are all these nodes in the neural network? Those are all scalar values in matrix multiplication. All the lines are matrix multiplication operations. So you have input times weight, add a bias, activate, repeat, input times weight, add a bias, activate. That's it. It's just repeating the same set of math operations over and over and over and over again. Those layers, what's inside the neural network, now that's the topic of many, many PhDs. What are inside all of these layers? Well, they're just matrix multiplication operations. Now, what did we just learn about quantum circuits? What are inside of quantum circuits? Inside of quantum circuits are matrix operations that apply to quantum data. Do neural networks apply to quantum data? Do we look at neural networks as the quantum function approximators as they are? Not necessarily, not normally. One more idea that I want to show you before I tie literally everything in this stream together into one beautiful aha moment for you. A nice little, eureka moment for you. And okay, we talked about deep learning. We talked about quantum circuits. There's one more idea, and that's the idea of the kernel method. So in machine learning, there's this idea of the kernel method where you have some high dimensional data with like 1 million data points, and it's just going all over the place. The kernel method, we have data in 15 million dimensions, and let's just, a bunch of colors for different dimensions. That's our data. What we want to do is we want to turn it into linearly separable data so we can run a simple support vector machine or some simple function on it. And so the way to get there from high dimensional data to linearly separable data is the kernel method. Now, there's a lot of ways of doing that. And I just wanted to briefly mention that so I can talk about the last part of this. And the last part of this is this. And that's the idea of a quantum neural network. The idea behind a quantum neural network borrows from ideas from deep learning and from quantum circuits and from kernel methods. The idea is that we start off with an input I. That's our starting input. We then give it to a quantum gate. So let's just say it's Q, okay? And then it's got an output, O, okay? Inside the quantum gate are quantum parameters. Normally, we optimize those parameters using gradient descent, using neural networks. But, that's exactly what we're going to do right now. Normally, we run all this on a classical computer, but in this case, we're going to optimize using a classical computer. We're going to optimize quantum parameters. So this is a differentiable function. And optimization, opt, is going to happen classically on the quantum circuit. So the quantum data, the quantum structure, that there's no gradient descent happening with that quantum math. the gradient descent is being computed using the classical computer, but it's updating our quantum circuit. So it's like a hybrid quantum classical neural network, if that makes sense. And it probably doesn't make sense because there's a lot that's still to make sense. I mean, there's so much theory to go into when we're talking about quantum neural networks. But luckily for both you and I have this wonderful library called PennyLane that I'm about to show you that was created by Xanadu.ai. So let me show you the PennyLane library. PennyLane, obviously named after the Beatles song. And it's basically a way to get started on your quantum machine learning journey. What I really love are all of the applications, the documentation they have. Amazing stuff. I love to see that. And they've got all sorts of examples. And I just love to see that. So PennyLane is essentially a Python library built on other quantum computing libraries like QI-Skit from IBM, TensorFlow Quantum from Google, D-Wave, one of my previous clients. I'll probably work with them again at some point in the future. Love D-Wave. Shout out to D-Wave. Yeah, I mean, this is awesome. You could sit here and learn this stuff all day. And basically what I did is I basically hacked together this really simple 37-line quantum circuit. And basically, we can run it right now. Let's just make sure that it runs. Bum, bum, bum. As you can see, the cost function, it's minimizing the cost over time, optimizing 2 parameters. What this is doing is it's saying, make it bigger. Bigger. Cancel. Okay. What it's doing is saying import PennyLane and then import NumPy. They've got their own version of NumPy. And then we create this quantum machine learning device, all right, which is going to be this simulated qubit because we don't have an actual qubit. This is running on a GPU. Then we create a quantum circuit. Now, inside the API, there are all sorts of quantum circuits. The Pauli circuit, you've got the Hadamard. These are all quantum logic gates, and there's about like 10 or 12 of them, about a dozen of them. A lot of them are reused. Some of them are, reusable because you use them for things like putting some values into superposition, which you will need often in quantum computing, or to rotate a certain set of qubits across block space, Hilbert space, or something like that. And so nothing really special. I just chose these random circuits. That's essentially what deep learning is like, just messing around with random linear algebraic operations until you break some state-of-the-art result, right? And these are the initial 2 parameters, 0.54 and 0.12. There's a cost function, which is kind of black boxed away for us. But essentially, it's using gradient descent, as you can see here. And then the training loop is only 5 lines long. We're just saying, optimize that circuit using gradient descent on our classical computer. And it does that. Like, it starts off, it just knows that it needs to get to these 2. Those are the supervised nodes. And then starting randomly, it's going to iteratively compute what the parameters for that qubit should be. So is that important for us? I mean, do we care what do we care about rotating a qubit? No, not necessarily. What we care about is making Bitcoin's network quantum resistant. And that means we have to solve the prime factorization problem. Shor's algorithm does that, given a powerful enough quantum computer. Does one of those exist yet? Not to our knowledge, because it requires stability over a long period of time. It requires quantum error correction. One of my good friends is working at the Google Quantum AI Lab right now on that problem. He's very enthusiastic about it. He's very excited about it. And so I am too. And in a few years, we're going to see this happen. But right now is a time to start practicing these algorithms, seeing what the results are, trying to see if we can solve anything useful. And I think one of the most useful areas of research for independent enthusiasts like myself and hopefully like you are in one-shot learning, because not everybody has access to the data. And as sexy as algorithms are, they are a commodity. The real value of machine learning comes with the data. He or she who has the data controls the world and controls the future. So we wanted to create models that require less data. And these ideas of superposition, the amazing tool set of Hilbert algebra, and the amazing tool set of quantum hardware, quantum qubits, physical qubits, are accessible to us via cloud solutions like D-Wave, like QI-Skit, and we can access them using PennyLane or TensorFlow Quantum. All right, let's get to the last question, and then I'm gonna answer some more questions. So the last question is, which of the following functions are not differentiable? Okay, and so the 4 possible answers are neural networks, quantum circuits, language models, or y equals 1 over x. Now, I'm going to give you guys a hint while we look at the answers that are coming in as to what the word differentiable means. Calculus is such a beautiful, it's probably my favorite math, because calculus tells us the direction that something is moving in. And that something could be a car, it could be a plane, or it could be the direction that a system is learning in. And when I say direction, there's a number 0 and there's a number 1. And there's infinite space between those numbers in a continuous setting. Let's say we have a value. It's moving more towards 0, it's moving more towards 1. How do we know what direction it's moving towards on the timeline? Calculus. Calculus not only tells us the direction of scalar numbers, calculus tells us the direction of quantum gates. It tells us the direction of superimposed states. It tells us the direction of quantum state vectors that are using Hilbert algebra to create new quantum state vectors. It tells us where in the block sphere it might, and here's my thought, and here's an active area of quantum neural net research, it might even tell us which universe to be using when we're computing the results of our quantum ML algorithms. That's crazy. That's crazy to say. I mean, this is such an existential area of computing. So awesome, so interesting. I can't wait. Google's going to be the one to do this, by the way. Google's quantum computer is going to be insane. Or D-Wave. I have to give a shout out to D-Wave, my client. So let me answer 2 more questions, and then we're going to announce the winner. They're going to win $500, and then I'm going to do a freestyle rap for the winner. Why does quantum machine... Wonderful Vumsies asks, why hasn't quantum machine learning taken over the world? Because as cool as it is, it's not doing any of its promises. It's not offering low shot learning. It's not offering data efficiency. It's not offering, because we don't have a stable enough quantum computer, right? We can get enough qubits. It's not just about enough qubits. We need stability. We need to minimize decoherence. We need to minimize leakage of information from this isolated quantum computing environment. Remember, guys, when you measure something, that's when you get the answer. I miss talking about, there's so much to talk about. I miss talking about the idea of quantum probabilities. We have probabilities, right? 20% chance of rain, 30% chance of sun. In the quantum world, there are negative probabilities. There are simultaneous probabilities. And so we don't use probabilities to define them. We use amplitudes. Amplitudes are essentially quantum probabilities. And they're like placeholders for actual probabilities. And once we conduct a measurement doesn't have to involve conscious states. It can involve a machine, doesn't involve but once anything or anyone measures some value, instantly, all of those possible values collapse to 1. That superimposed state collapse to 1 single value. And so there's a lot of techniques around when to measure, how to measure, what's the timing, how to structure the superimposed states. And that's really the beauty and the theory of quantum machine learning and quantum computing more generally. But none of that matters because we don't have a good enough quantum computer, and that's why it hasn't taken over the world. But I believe that in the next 5 years, absolutely, we're going to see something amazing come out of quantum machine learning, just because there are enough smart people working on it, and hopefully you as well. I think this would make an amazing project to work on. I think it would impress a lot of people, so definitely do that. Second and last question before we answer this question and announce the winner. The last question is, can you show us the results of the quiz at the end of the stream? Okay, Yves, for you, I will do that. And last statement, Ayula says, quantum neural networks equals time machine. I guess, but we can't go back in time. We cannot go backwards in time. Only sideways and maybe forwards, but not backwards. In that way, it's a time machine. Let's see what the answer was. The answer, guys, was is y equals 1 over x. This is a non-differentiable function. What that means is that we cannot use calculus to find certain values. Certain values are going to be impossible. For example, if we try to differentiate 1 over x using the power rule, that's going to be not an answer. We can't do that. That's impossible. So we'll hit a singularity. So differentiation. So how do we differentiate x squared? We use the power rule. We take the power at the top, we multiply it by the coefficient, and then we subtract 1 from the power. So the differentiation of x squared is going to be 2x. The differentiation of neural networks can be differentiated. They're universal function approximators. Quantum circuits can be differentiated using classical computing. Language models can be differentiated using whatever model they're using, probably a neural network. Y equals 1 over x cannot be differentiated. So what we're looking for, guys, are differentiable functions. And the reason is so that we can find what direction they can learn in, so we can find an accurate prediction. That's why differentiation matters. That's why deep learning works. That's why backpropagation works. Now, let's see who the winner is. Oh, there's one more there's actually 2 really interesting questions. I have to answer these questions and then we're over. Harshit asks, can you throw some more light on quantum stability for a long time? Challenges in quantum computing hardware as of today. I would love to. So, when I visited D-Wave in Vancouver, they invited me over, and they showed me their quantum computer after like 2-3 levels of security. They're using supercooling to bring that quantum system to a superimposed state. So the type of metal they're using is niobium. A lot of different ways to create this superimposed property. How do we superimpose these electrons? And then how do we engineer that superposition? Very fine, delicate process that requires near absolute zero temperatures and certain types of metals that can superconduct properly. That's what they use, niobium and like negative 250 something degrees Fahrenheit. Is it perfect? No. And because it can only stay stable for a certain amount of time before there's leakage. And leakage means maybe there's this is going to sound crazy. Maybe there's a human who accidentally looks at the result before it looks. Instant leakage. That's going to mess everything up in the system. Maybe it's like a non-human. Maybe it's like a clock that's somehow measuring the results in some way. Instantly, it's going to leakage. There's leakage, and so the superimposed states collapses. So the wave function collapses. The Schrodinger's equation collapses. So it sounds crazy, but we have a hard time creating isolated environments that don't have any kind of observation happening. If we can do that for a long period of time, then we can create a stable quantum computer. Last question. What if 2 observers see a quantum system at once? Arnav asks. Is it certain that they would measure the same thing? Will the wave function collapse be the same for them? Certainly. If 2 observers look at it at the same time. I didn't see that in the Feynman lectures. That's a really interesting question. What if 2 observers look at something at the same time? I would think that the wave function collapses based on any one of them. It doesn't matter if it's 1, 2, or 3. As long as any observer or a machine or a clock or a measuring device of any kind. So it doesn't matter. It will collapse. Really finicky, not stable, these superimposed qubits, as we've seen in the literature. Some of the best papers on this are coming out of Google Quantum AI, Quantum Neural Networks. Guillaume Verdon is an author, my friend, who wrote some of the best ones on that. I would definitely recommend checking out his work on this. I love this stuff. I'll probably make a lot of videos on this over the next few weeks. Definitely be going live. Let's see who the winner is, guys. It's time to see who the winner is. Yves asked if we could see the results. So let me show you guys the results while I look at them too. Transition. Okay, here you go, guys. So the winner is... Who got first? Yoshi City YC. It was the first one to get all of them correctly. All right, Yoshi. That's what I like to see. Yoshi City YC wins $500 in cash, Bitcoin or Ethereum. Doesn't matter. Their choice. They win this competition. Congratulations to Yoshi. You win Victory Royale. You are the winner. Congratulations. Everybody congratulate Yoshi. And now I'm going to freestyle a song for them. Yoshi, my king. This video is dedicated to Yoshi City. Yoshi, I want you to send me an email, hello@surajraval.com. I want you to take a screenshot of your screen and email me that. And I want you to do that in the next hour. So you have 1 hour to send me that email. If anybody tries to phish me, I will hack you. That is a threat. Okay, I know nobody's going to do that. But Yoshi, definitely send me that email. And I'm definitely going to work on security for this and make it more efficient every single week. All right, so we'll have dedicated accounts and it's going to get more and more efficient. So Yoshi, my king, congratulations on solving that. Let's play this tune for you. Winter Sun, da da da. Play the tune. Here we go. Yeah. Is this playing? I'm not even sure if it's playing. Yeah. I guess it's playing. Yeah. I guess it's playing. The mind is a muscle, so you break logic doors. The mind is a muscle, so you break logic doors. The mind is a muscle, so you break logic doors. Mind is a muscle, so you break logic doors. Hey Yoshi, I guess you stepped up on my platform. You got all my questions right. How you do it, Mac on. You Mac on my questions one by one. I showed you PennyLane, and then you stepped back on. I showed you my quantum gate. I showed you my quantum circuit. I showed you my neural network. You look at, you made it, and you made it work it. You worked my circuit to the end. I got my superimposed state one by one. I try to get my quantum vector up in Hilbert, one and done. Hilbert space is what they call it. It's that complex space, out of mind, out of sighted. Yeah, quantum shorts, factoring algorithm, that's what I like to do. On my quantum network. It's not me, I guess it was you. Superimposed across time and space. That's my timeline. I guess you could call me Jace. No, fuck that. My name is Siraj, the one and only. I'm not a mirage. I try to bring you everything one by one. I try to show you the secrets of the universe. It's one and done. Quantum gates are optimized classically. Every single gate is a superposition, don't you see? Hey Yoshi, I can't believe you won, man. You're my hero. I love you. All right. Thank you, Yoshi, for playing. Thank you, everybody, for playing. I love you guys for being here today. We're going to do this every single week. Guys, we have a game. I have a game coming out, Code Royale. I can't wait to release that. I'm super excited. I'm going to be doing these live sessions every week. I love doing this. I love being here with you. Seriously, thank you for being here, guys. I really love you for being here. It means a lot to me. And I am going to really focus on improving these live streams every week, making sure that they're as valuable as possible. Yves, I heard you that you wanted to get the Jupyter notebooks. I'm going to continually add documentation and code to the video description to help you guys. Guys, please go out there and do a quantum machine learning project. Use PennyLane. It's much easier than you would think, and you're going to feel really smart. I promise you afterwards, all right? So thank you for being here, and I love you. Peace.